Well, good morning. It's really glad to see a big group like this get back together on the second day. If you came back, I presume you enjoyed yesterday's talks. There was a lot of enlightening information and great presentations given yesterday, and of course, last night was a tremendous celebration. My name is Adam Hamilton. I'm the president of Southwest Research Institute here in San Antonio. This year we'll celebrate our 70th anniversary. And today you'll hear from one of our staff members. But first I wanted to just thank you for being here again and welcome you to the second day of our conference. Yesterday we heard about challenges, and there are many challenges indeed that we are well equipped to address in the state of Texas. Many different skill sets from science, engineering, medicine, and technologists can all come together and contribute to the solutions that we are pursuing for a better and more sustainable future for Texas. So this morning I'd like to introduce you to Dr. Bapiraju Surampudi. Bapi is a staff member at Southwest Research Institute. He's worked in the area of vehicle powertrains and controls and electrification for over 20 years, almost 25 years now. His experience spans light duty, which as you heard yesterday includes what most of us interact with every day, to heavy duty and combat vehicles. Various technologies he has developed encompass the areas of hybrid powertrains, which we also heard some about yesterday. Dr. Surampudi will give us a little bit more detail on what hybrid powertrains are about and about some of the other developments in the electrification of vehicles to include the light duty, heavy duty, other fleets, and other types of transportation assets. Dr. Surampudi also has a lot of expertise in lithium-ion battery technologies, fire control systems, and autonomous vehicles. He is a senior member of IEEE and a member of SAE. He received his PhD from Texas A&M University at College Station. Dr. Surampudi.
Thank you, Adam. Good morning, ladies and gentlemen. So we've seen some great talks yesterday. I've really enjoyed the morning session. So today's focus with this talk is vehicle electrification and some of the trends that are present today and where we think the future is in this area. Southwest Research Institute is an independent applied R&D laboratory located in San Antonio, Texas. So those of you that have this afternoon some time off, you're invited to come by. If you need to contact one of our staff members for a tour, we'd be very glad to accommodate that. So Southwest Research deals with everything, technologies from deep sea to deep space. You can see the Alvin underwater submersible on the left side there that can cover 90% of the ocean floor to recover objects in deep sea. And we span all the way to space. We've led the mission to Pluto, the New Horizons mission. And of course, we deal with everything in between. From geological engineering, robotics, pharmaceuticals, engines, vehicles, communications, defense, and intelligence solutions. On the advanced electric vehicle research that's happening at Southwest, we build battery packs. So we take lithium-ion batteries that are produced by major cell manufacturers today and assemble them to make battery packs that go inside vehicles. We deal with lubricant technology for electric vehicles. We deal with safety of electric vehicles, sensor technology for batteries, state of charge, state of health, and so on. And then we look at battery integration with the grid. In the future, vehicles could be a form of energy storage that's very flexible and supportive to the power generation industry. I think we may have a clicker issue. So Southwest Research Institute is a global leader in the number of technical consortia that it leads. So a consortium is a group of commercial industries coming together to explore pre-competitive technology. And Southwest leads many technical consortiums. In the electrification area, we benchmark electric vehicles. You can see a few examples there. The GM EV1, the Chevy Bolt, it starts with the letter B, Bolt, not the Volt. So that has been released a couple of weeks back in the states of California and Oregon. We are benchmarking that this year. And you can see the Volkswagen e-Golf and the Tesla Model S there. One of the consortium picture is shown on the right where the members are inspecting the parts of an electric vehicle. So let's just go through a history. It's always nice to get a perspective of where we've been and what the road ahead could look like. So you can see the cycle, just like the cycle of life. There's a cycle for technology. Here you can see the waxing and waning of electrification over a period of last 100 years or more. So you can see each quadrant of this circle represents one phase of the cycle. So let's start at the beginning. The battery electric vehicles were invented by Robert Anderson from Scotland, England, in 1832. And they came to political limelight when President Taft made one of the Baker electric runabout vehicles as an official White House vehicle and reached their peak sales in 1912. You can see 37% of the market share of vehicles was electric. It's very interesting to see that at that time, most of the vehicles sold were steam-powered vehicles. And the internal combustion engine was still one of the research areas in those days, primarily because people had to manually start these vehicles, and it was not very pleasant. As with everything, once they reach their peak, they have to see a decline for some time. And the first decline, paradoxically, happened because of another electric machine, the starter, that was invented in 1912. So people didn't have to crank these vehicles manually anymore. And that made it very, very comfortable to own these internal combustion engine-driven cars. And then we had the oil price, the boom of the 1920s. You can see a couple of young oil tycoons there in Houston. Together, these two events in history led to the first extinction of the electric vehicle in 1935. So then, for 40 years, the internal combustion engine pretty much ruled the market. And there was no impetus for electrification from any private entity or even the governments until 1970s, when the world gave us the Israeli-Palestinian conflict. And that made oil a very, very dear commodity in those days. That, along with some of the regulations, the corporate average fuel economy, the CAFE regulations, and California's zero-emission vehicle, ZEV regulations, together led to the development of the GM electric vehicle 1 and the Toyota Prius hybrid in the late 1990s. So that was the next rise of vehicles, and inevitably, we're going to see oil price then hit the electrification trend again. We saw low oil prices. That led to a loss of R&D activity in electrification, but this time it didn't go to extinction. It went to some low-key activity. Following that, well, guess what? $145 a barrel of oil hit the markets, and that created a very great renewed interest in electrification. And then we saw a fleet of electrified vehicles from the major automotive manufacturers. We all know the Nissan Leaf in 2011, Tesla Model S, and then the Chevy Bolt that came out 2 weeks ago. Keeping in step with these cycles, so the last 10 years we are on the ascending path of electrification. The battery technology kept in step with it. The first cycle saw the lead-acid batteries being the dominant player, and followed by nickel metal hydride batteries, which could store 4 times the energy that lead-acid batteries could store. And in this cycle, we're seeing lithium-ion batteries, which could store 8 times and higher energy density or amount of energy inside the battery. So, well, this is all well and good. There's regulatory, political considerations for the cycling. So, but technically speaking, why do we need to electrify? What's the motivation for car manufacturers to electrify vehicles? Well, when we go to a dealer, we see a sticker on the window which says this is the miles per gallon that you're going to get when you drive this vehicle inside the city. And how is that number derived? EPA basically runs a special city driving cycle that's shown down there that has a very low average speed, 20 miles per hour average speed. And whatever fuel is consumed for these 7-mile cycle, they come up with the miles per gallon number. And you can see where is the engine operating for this cycle. The graph on the top has the engine load increase on the x-axis, and where the engine is operating in terms of its heat balance on the y-axis. So the engine is very efficient if it's in the blue region, and all the red regions are the losses. So, well, this 20 miles per hour is keeping the engine at the low end. And so the losses are quite high. And when we electrify, guess what we do? We downsize the engine and load it up better. And that makes the engine operate much more fuel efficiently, and so our miles per gallon numbers go up. So what other factors from fuel economy impact electrification? Air quality, regulations from California and the EPA, and then the consumers. Well, in the end, we are the ones that dictate if we want electrification or not. And that is based on total cost of ownership. So the markets always want to be in that red zone there where there's an intersection of all these 3 forces. So let's look at emission regulations. If you look at fleet emissions, there is a push in the next 8 years to reduce the ozone compounds in the exhaust of internal combustion engine vehicles to be reduced by 4 times. The US actually has the most stringent standards on the planet. And it's very interesting. If you look at certain states, the technology has advanced so much that cars actually are putting out cleaner air through the exhaust than they're sucking in through their intake. So they're like moving filters. On the fuel economy regulations, if you look at the sales-weighted miles per gallon, for the last 8 to 10 years, we're on an innovation slope of 0.65 miles per gallon every year. So there's advances in technology on the internal combustion engine that's putting us on that slope. Well, to reach the corporate average fuel economy number by 2025 of 54.5 miles per gallon, well, we have to triple the rate of innovation in the next 8 to 10 years. And, well, that's a tall order. So electrification will be one way to meet that slope. The second factor is pricing, gasoline pricing. We've heard great insights yesterday on what drives these prices. We are at a locally low price in this global picture of gasoline prices, driven by industry that is within the US, the fracking industry, and perhaps some of the political considerations in the Middle East. The second factor is the lithium-ion battery prices themselves. They have been dropping almost 2 times every 8 years. And so once we reach a number like $80 a kilowatt hour, then the electric vehicle pricing will get as attractive as internal combustion pricing. But we have to be complete with the picture to look at the scars left behind by lithium mines there. You can see one of the lithium mines in South America, and it's like a scar on the face of the earth. So that has to be managed a little more responsibly. If we look at hybrids, we go from mild to all electric vehicles. The mild hybrids at the left end of the spectrum will give us low CO2 emissions, not as low as the full electric vehicles, but they can run at low voltage, 12 volts to 48 volts, and the cost of electrification is not so high. So the return of investment for the consumer is pretty good on the mild hybrid side. But as we go to full hybrids, we're getting to 300 to 400 volt range. And the battery packs are bigger, the electric motors are bigger. So the price of a hybrid vehicle is much higher. But we do get better CO2 reduction and better miles per gallon. And of course, we know the Chevy Bolt and the Tesla Model S, the full electric vehicles, they don't have an internal combustion engine. And they're primarily serving the luxury car segment these days. But as the battery prices come down, we can perhaps be much more reachable to the average consumer. If we look at mild hybrids, the electrification opportunities, where do they lie? Well, there's a lot of accessories on an internal combustion engine, like the air conditioning compressor, the alternator, the oil pump, and so on. If we take these out and electrify, then we can downsize the engine, and the engine can only be focused on propelling the car, rather than serving all these loads. If we look at a full hybrid, this is a GM Chevy Volt Generation 2 plug-in hybrid electric vehicle. The battery pack is quite large. It's a T-shaped battery pack that you can see at the bottom of the vehicle. And there's an onboard charger and a charger port that can charge this battery when you come home. And the big electric motor that's seen by the side of the internal combustion engine allows the engine to be much smaller. You can drive with this vehicle to work and home up to 50 miles in an all-electric mode, so you don't need to turn on your engine at all. So why don't we see electrification proliferating in this current cycle? What are the barriers that are stopping it? First one is, of course, cost. The battery cost is close to half the cost of the electric vehicle. Well, we need that to come down. The next one is temperatures. Car manufacturers have to sell the same car in North Dakota and Arizona. So it impacts the battery life, and it impacts the driving range. We heard of range anxiety yesterday, which is getting less and less with the newer electric vehicles, but it's still there. So you need special thermal management systems on batteries to be able to alleviate these problems, and that drives up the cost further. Well, with every technology, we need it to be safe. The fires of lithium batteries are different in nature compared to gasoline and diesel fires, so firefighters have to be trained carefully. And this is also a reflection of a human attempt to pack as much energy into batteries as nature packed with dinosaur fossils into gasoline. So crude oil, nature only took about 200 million years to pack all that energy under the earth, and we're trying to do that in 100 years. Southwest simulates a vehicle crash with special test rigs. We can see a hydraulic test rig here. On the left side, we can see a piston that is pushing on the battery pack. The graph below is telling us how much force is being used to push to emulate a crash in a vehicle. And the picture on the right side is the thermal camera that's looking at the temperatures inside the battery pack. And you will see some bar charts that will come up that measure thermocouple temperatures at different parts of the pack. So, of course, everything that's man-made can be made to fail. You can crush it, or you can push it to its design limits and make it fail. What does it mean? Really, what it means is that we can understand the limits to which a particular design will work, and we can improve the design of the frame around the battery pack to avoid being compressed to those critical levels. So this kind of testing improves the safety of electric vehicles. Lack of infrastructure. Well, we're so used to having a gas station every couple of blocks, or maybe not a couple of blocks, but every few lanes, every few corners of the city, that we want and expect public chargers to be almost matching up to that level. Well, unfortunately, we have 1/5 that number on public chargers. The next one is, how long do we want to wait at a gas station to charge our vehicle? Well, the fastest charger today, the state-of-the-art charger from the Tesla, is taking 60 minutes to fully charge the battery pack compared to 2 minutes on the liquid fuel. So we got a long way to go before we can speed that up. So on the trends, what are the car manufacturers doing today? Well, they're first focusing on improving fuel economy and the electric range and the total range of vehicles. So you can see the mild vehicle on the top and the fully electric vehicle at the bottom. The Mercedes 2017 S-Class is a mild 48-volt vehicle that increases the fuel economy at up to 15%, at a very low increase in electrification cost. And then we have the Honda full hybrid that not only makes a good fuel economy, but also gives us reasonable amount of power and a total range, including gasoline range, more than 300 miles. And then we see the Chevy Bolt. This is supposed to be a barrier breaker for electrification. Came out 2 weeks ago, innovation from General Motors, close to the sweet spot of 250 miles. So the range anxiety may not be so present for this vehicle. And the price is not so high. Of course, it's still high compared to a gasoline or internal combustion engine vehicle comparable, like the Chevy Spark, which costs about $17,000. On the performance side, on the fun side, racing enthusiasts and acceleration enthusiasts love electrification because even at very low launch vehicle speeds, you can truly feel like you are inside a rocket. It's like the Tesla Model S takes about 2.4 seconds, the latest one, to go from 0 to 60 miles an hour. Well, you can get a thrill from that. And on the commercial side, for a long commute and city commute, your routes are all so determined that you can predict exactly when you're going to hit what kind of slope on the road, when you're going to brake, and so on. So you can really optimize the control system for maximizing fuel economy. And then refuse trucks, garbage trucks have special needs that can benefit from electrification. Fleets can benefit with very low investment into electrification, huge fuel savings. And freight vehicles, they have special routes that they have to take inside cities where cities are getting more and more stringent with pollution. So you can just work these vehicles just pure electric mode inside cities. On our waters, tugboats in the Houston harbor can pull huge ships inside the harbor with very low pollution by turning off their engines. These electric tugboats are very nice. And then on the luxury segment, catamarans can silently charge your battery packs with solar panels. And big cargo ships, they have big diesel engines that are polluting and requires a huge amount of fuel to be carried on the cargo ship. So you can make the amount of fuel to be carried less by electrification. On the off-highway side, we all know lawnmowers that we want without plugging into a wall, so we want batteries on there. Precision agriculture with GPS can benefit from electrification. Mining, logistically, they don't need to ship lots of fuel to the mining sites, and they can minimize emissions under trapped mining volumes. Construction equipment. So where's the projections? The battery prices are shrinking. They're expected to drop almost to $80 a kilowatt hour by 2030. This is a Bloomberg prediction, and Southwest agrees with it. Price reduction by volume. This is the Gigafactory in Las Vegas from Tesla and Panasonic. The battery price gains are always passed on from the car manufacturers to the end consumer. Here you can see the GM Chevy Volt 2013 to 2014 reduction of $5,000 being passed on to the consumer. And the sales, if we assume only regulation is going to drive this, will reach about 1 million pure electric vehicles by 2025. That's the prediction by Department of Energy. This is the official government prediction. This is assuming the consumers are not interested in buying vehicles, and this has to be driven purely by regulation. So the actual numbers will be bigger than this. So today, it's all about regulations and politics. That's what's driving electrification, the biggest factor. And tomorrow, are we going to cycle the technology again? Are we going to slow down, or are we going to accelerate? And this is driven by the three factors we looked at about regulation, consumer pricing, and politics. The wars in the Middle East and everything else like that. So that's where we are. Thank you for your attention.
Thank you, Bapi. It's a very enlightening, energizing presentation, if you'll forgive me. Do we have time, Steve, for just a couple of questions? Anybody have a question for Dr. Surampudi? Yes.
One thing you didn't mention was autonomous vehicles, and how are they going to change value proposition for electrification?
A very good question. I think I need my mic back on. Okay. Autonomy and electrification are synergistic technologies. So that's why you see Tesla, for example, trying to put an autonomous feature into their Model S and other Model 3 vehicles. So autonomy is mainly driven by legal issues. The technology is already there. The pricing is on its way down, like the battery prices. So theoretically, we could have an autonomous vehicle ready with electrification on board. And Southwest actually worked on an autonomous vehicle 20 years ago. We've demonstrated it was all feasible within a reasonable price. So I hope I answered your question.
Okay, do we have one additional question?
So a world-class dragster will go over 100 miles an hour in less than 1 second, okay? In less than 1 second, okay? I grew up with that. You going to match that?
Well, with the electric motor, certainly we can match it. But I think on the consumer acceptance side for vehicles, that there are safety issues that will prevent us from actually implementing it on mass vehicles. So the electric motors are able to generate huge amounts of torque at low speeds. And batteries, lithium-ion batteries especially, have a large discharge power capability at fully charged condition. So they can really enjoy taking off into orbit.
Any additional questions?
Can you tell me what the number of deep cycles lithium-ion batteries can run on these days? All the way down, all complete discharge and recycling?
Cycles? Yes. So if you look at hybrid vehicles, we have what is called a shallow depth of discharge. So if you look at a Toyota Prius.
Total discharge is what I'm interested in.
Total discharge? So if you look at the Model S, we're looking at the old model was about 90 kilowatt hours. So the total energy capacity of the battery was 90 kilowatt hours. If you're driving like within a city, you can get up to 240 miles. We've tested this vehicle at Southwest. But if you're aggressive and you're driving on slopes like you are fighting a war, then you can cut it down to maybe 60 to 70 miles.
I'm talking about the number of deep cycles the lithium-ion batteries are capable of. How many times can you completely discharge and recharge them?
It varies with the chemistry, okay? So if we look at
State of the art.
What's that?
State of the art.
State-of-the-art NCA, nickel, cobalt, aluminum chemistry. That's the most energetic chemistry. So that can last, if you're really aggressive and didn't design your voltage limits, take it all the way to Vmin and Vmax on the voltages, then you can kill the battery in maybe 3 months. And that's maybe, it varies to 200 cycles to 300 cycles. But the automotive designers don't actually push it all the way to the limits. They conservatively design the limits and increase the pack size so that you actually can minimize warranty costs and live the full 10-year powertrain warranty.
Yeah, it could be thousands of cycles that could be on. Dr. Surampudi, thank you again for your presentation today and your comments. Very good. Thank you.